So, here's something worth thinking about as you settle in tonight. Right now, about 20,000 kilometers above your head, a small fleet of satellites is quietly sailing through the dark, each one moving at roughly 14,000 kilometers an hour, and each one is speaking constantly into the void. They're not speaking to each other. They're speaking to you. Every single one of them is broadcasting a faint, whispering signal down through the vacuum of space, through the ionosphere, through the clouds if there are any tonight, through your window, into the little chip inside your phone sitting on the nightstand beside you. And that chip is listening. It's been listening this whole time, even now, even as you're lying here with your eyes closed. It's catching whispers from 4, 5, sometimes 8 of these satellites at once. And from those whispers alone, it can figure out exactly where you are on the surface of the Earth, down to a few meters, in less than a second. No compass, no map, no landmark, just silence and starlight and math. You don't feel any of this happening. Nobody does. The signals are far too faint, the calculations far too fast, the whole system far too quiet for any of it to register as anything at all. And for most of human history, nobody had any reason to believe that something like this could ever exist. The idea that you could know your exact position on a spinning planet at any moment, anywhere, just by listening to whispers from space would have sounded less like science and more like a fairy tale. Tonight, we're going to talk about that fairy tale. Global positioning, GPS, the whole strange, layered, unexpectedly profound story of how humanity taught itself to always know where it is. We're going to take it slow. Start from the very beginning and just walk through it together, piece by piece. No rush. If you drift off somewhere along the way, that's perfectly fine. The satellites will still be up there in the morning, doing exactly what they're doing right now, whether you're listening or not. And honestly, some of this story makes more sense when your mind is loose and unfocused anyway, because underneath the technology, underneath the satellites and the receivers and the little blue dot on your map app, this is a story about something much older and much simpler. It's a story about a question that has haunted every traveler, every sailor, every lost soul in human history. Where am I? That's it. That's the whole question. It sounds almost embarrassingly simple. A child could ask it. And yet for most of the time humans have existed on this planet, it was one of the hardest questions in the world to answer with any real confidence. Let's start there, because that's where the story actually begins. Not with satellites, not with rockets, not even with electricity. It begins with the stars, and with people who had absolutely no way of knowing where they were, floating on an ocean that all looked exactly the same in every direction. Think about what it must have been like. You're on a wooden ship somewhere in the middle of an ocean that stretches farther than you can see in any direction. There's no shoreline, no mountain to orient yourself by, no signposts, just water and sky and the slow creak of the hull. If a storm blew you off course for even a few days, you might genuinely have no idea whether you were 100 miles from land or 1,000. People died this way. Entire ships vanished this way, not because of monsters or mutiny, but because of something as unglamorous as simply not knowing which direction to sail. For centuries, the smartest minds in navigation worked on this problem from every possible angle. They looked at the position of the sun at noon. They tracked the North Star. They used instruments called astrolabes and later sextants to measure the angle between a star and the horizon. which could tell you your latitude, how far north or south you were, with reasonable accuracy. Latitude, it turned out, was the easier half of the problem. The stars are honest about latitude. The angle of the North Star above the horizon tells you, quite reliably, how far you are from the equator. But longitude, how far east or west you are, that was a different beast entirely. That one resisted solution for centuries, and we'll get to why, and to the almost absurd lengths people went to in order to solve it, in a little while. For now, just sit with this feeling. The feeling of being somewhere, but not knowing where. Of looking around at a horizon that gives you no answers. That feeling, that specific ancient anxiety, is the thread that runs all the way through this story, from wooden ships in the 17th century to the phone resting quietly beside your pillow tonight. Every technology we're going to talk about tonight, every satellite, every atomic clock, every strange twist of relativity exists for one reason and one reason only: to answer that same simple ancient question a little more precisely each time. Where am I? And it took nearly the whole of human history and one very unexpected beep from outer space to finally get a satisfying answer. Let's go back to the beginning of that answer now. Not centuries ago, but a little over half a century ago, to a cold October evening in 1957, when a group of American scientists sat around a radio receiver in Maryland and heard something in the sky that changed everything. Let's slow down here, because this part of the story deserves a proper look before we move on to satellites and space. For most of human history, navigation was less a science and more a very educated guess, stitched together from experience, memory, and a fair amount of luck. The earliest sailors, thousands of years ago, navigated the way you might navigate a familiar neighborhood in the dark. They memorized coastlines. They knew that if you kept a certain mountain on your left and sailed for a certain number of days, you'd reach a certain harbor. This is called piloting, and it worked beautifully as long as you stayed close to land and as long as nothing unexpected happened. But the moment sailors pushed out into open water, out of sight of any coast, all of that memorized knowledge became useless. The ocean doesn't have landmarks. It has waves and more waves, and after a few days they all start to look the same. So navigators turn to the sky. The stars, unlike the ocean, are reliable. They rise and set in predictable patterns, and a clever observation made by ancient astronomers gave sailors their first real tool. The height of the North Star above the horizon tells you your latitude, your distance north or south of the equator. The instrument they used to measure this evolved over centuries. First, the astrolabe, an elegant brass disc that could measure the angle of a star above the horizon. Later, the quadrant. Later still, in the 1730s, the sextant, a beautifully precise instrument using mirrors that could measure that same angle far more accurately, even on a rolling, pitching ship. With these tools, a sailor could determine latitude with real confidence. If you know you're at, say, 30 degrees north, you know you're somewhere along an invisible line that circles the entire globe at that latitude. Not perfect, but genuinely useful. Longitude was the nightmare. Here's why. Latitude is anchored to something fixed and universal, the tilt of the Earth's axis relative to the stars. But longitude is arbitrary. There's no natural zero point for east and west, no star that tells you how far you've traveled around the planet's rotation. Longitude is fundamentally a problem of time, not angle. And for a very long time, nobody quite understood that, let alone had a way to solve it. Here's the insight that eventually cracked it open. The Earth rotates a full 360 degrees every 24 hours. That means it rotates 15 degrees every hour. So if you know what time it is at your home port, say London, and you can figure out what time it is locally, based on the position of the sun, you can calculate the difference, and that difference tells you exactly how far east or west you've traveled. Simple in theory, nearly impossible in practice, for one very frustrating reason. You needed an accurate clock. A clock that could keep perfect time back in London, no matter how much the ship rolled, no matter how the temperature swung from freezing to sweltering, no matter the humidity of a tropical crossing. Pendulum clocks, the best clocks of the era, were hopeless on a rocking ship. The pendulum simply couldn't keep steady time. This problem became so severe, so costly in lost ships and lost lives, that in 1714 the British government offered a staggering cash prize, £20,000, a genuine fortune, to anyone who could solve it. This became known as the longitude problem, and it consumed some of the finest scientific minds in Europe for decades. The eventual solution came not from an astronomer, but from a self-taught carpenter and clockmaker named John Harrison, who spent literally decades of his life obsessively building a series of ever more refined marine chronometers, clocks accurate enough to survive a sea voyage and keep true time. His fourth attempt, a device small enough to fit in your hand, finally cracked the problem in the 1760s. It's a genuinely moving story. A man who quietly outthought the greatest astronomers of his age with nothing but patience and brass gears. And if you're drifting towards sleep right now, that's a fine image to drift with. A lone craftsman bent over a workbench for 30 years, slowly solving a problem that had stumped kings. With Harrison's chronometer, sailors could finally know both latitude and longitude with real precision. For the first time in human history, a person on the open ocean could say, with genuine confidence, exactly where they were on the surface of the Earth. It's worth pausing here to notice something, because it's going to become the central theme of everything we talk about tonight. The solution to "Where am I?" turned out to be its heart, a solution about time. Not maps, not compasses, time. Keep that thought gently in the back of your mind. It's going to come back again and again, all the way up into the era of satellites and atomic clocks. The whole story of navigation, it turns out, is secretly a story about clocks. For the next 2 centuries, chronometers, sextants, and increasingly refined maps served humanity reasonably well. Sailors and later pilots learned to navigate with tools that, while imperfect, were good enough for the pace of the world at the time. But that pace was about to change, and it would change because of something falling out of the sky over the Soviet Union in the autumn of 1957. Something small and beeping and about to rewrite the entire question of what knowing where you are could even mean. October 4th, 1957, the Soviet Union launches a small metal sphere into orbit. It's called Sputnik 1, and it's almost comically modest by today's standards, about the size of a beach ball, weighing just over 80 kilograms, carrying nothing more sophisticated than a radio transmitter and a couple of batteries. But it is, without exaggeration, one of the most consequential objects ever built by human hands, because it is the first artificial satellite in history, and its faint, steady beep transmitted on shortwave radio frequencies that amateur radio operators around the world could actually pick up sent a wave of anxiety through the United States that historians still study today. The fear wasn't really about the satellite itself. It was about what it implied. If the Soviets could put a beeping metal ball into orbit around the Earth, they could, in principle, put other things into orbit too. Things far less friendly than a radio transmitter. But here's the quieter, less dramatic part of the story. The part that actually matters for tonight. While much of America was gripped by anxiety over Sputnik, two young physicists at the Johns Hopkins Applied Physics Laboratory in Maryland, William Geer and George Wyffenbach, were doing something much calmer. They were simply curious about the signal. They set up equipment to listen to Sputnik's beeps as it passed overhead, and they noticed something interesting in the pitch of the signal. As the satellite approached, the beeps were slightly higher in frequency. As it moved away, they dropped slightly lower. This is called the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches you and lower pitched as it drives away. Geer and Wyffenbach realized that by carefully measuring exactly how this pitch shifted over time, they could calculate Sputnik's orbit with remarkable precision, entirely from the ground, using nothing but the satellite's own signal. And then, almost as an afterthought, someone at the lab, their supervisor Frank McClure, flipped the problem on its head and asked a question that would quietly launch the entire field of satellite navigation. If we can use a known ground location to calculate an unknown satellite's position from its Doppler shift, he reasoned, couldn't we do the reverse? If we already know a satellite's exact orbit, couldn't we use that same Doppler shift, measured from an unknown location, to calculate exactly where that receiver is sitting on the ground? It's a simple flip, almost elegant in its symmetry, but it was the seed of everything that came after. Instead of asking, "Where is the satellite?" you ask, "Where am I?" given that I know where the satellite is. This idea landed at exactly the right moment, because the U.S. Navy had a very specific, very urgent problem that needed exactly this kind of solution. Nuclear-powered submarines, the Navy's newest and most strategically important vessels, could stay submerged for months at a time, silently patrolling the world's oceans. They carried a devastating deterrent, submarine-launched ballistic missiles, missiles that were only useful if the submarine launching them knew with absolute precision its own location. A missile aimed from the wrong starting point, even by a small margin, could miss its target by miles. But a submerged submarine has no view of the stars, no sextant readings, no landmarks. For weeks at a time, it navigates using something called inertial navigation, essentially very sophisticated dead reckoning, tracking its own movement through accelerometers and gyroscopes. And like all dead reckoning, small errors accumulate over time, drifting further and further from the truth the longer the submarine stays submerged. What the Navy desperately needed was a way for a submarine to periodically surface, just enough to raise an antenna, catch a signal from space, and instantly correct its position with high precision, then dive back down. Geer and Wyffenbach's insight, born from idle curiosity about Sputnik's beeping, was exactly the missing piece, and it led directly to the first operational satellite navigation system in history, a program called Transit, developed through the 1960s specifically to solve this submarine problem. We're going to spend some time with Transit next, because it's genuinely the direct ancestor of the GPS satellites orbiting above you right now. And because its limitations, the things it couldn't quite do, are exactly what later engineers had to solve to build the system your phone uses tonight. But it's worth just sitting with this moment for a second before we move on. A beeping metal ball, launched mostly as a political statement, overheard by two curious physicists who weren't even trying to solve a navigation problem, ends up seeding an idea that, 6 decades later, tells you your position to within a few meters while you're lying in bed, half asleep, not thinking about any of this at all. That's often how it goes in the history of science. The biggest ideas rarely arrive because someone set out looking for them directly. They arrive sideways, through curiosity, through someone noticing a small strange thing and simply asking, quietly, why? Before we go further into the history, let's slow all the way down and sit with the actual physics underneath all of this. Because once you understand this one core idea, everything else in this story, transit, GPS, the atomic clocks, even the relativity twist waiting for us later, will make a quiet kind of sense. Here's the idea, and it's simpler than you might expect. Light and radio waves, which are just a form of light our eyes can't see, travel at a fixed, unchanging speed. In the vacuum of space, that speed is a little under 300,000 kilometers every single second. It doesn't matter who's measuring it, or how fast they're moving, or what direction. This is one of the strangest, most stubborn facts in all of physics, and it happens to be exactly the fact that makes satellite navigation possible. Because the speed of light is fixed and known, something wonderful falls out of it almost for free. If you know exactly when a signal left its source, and you know exactly when it arrived at you, you can calculate exactly how far that signal traveled. Distance equals speed multiplied by time. It's the same formula you probably learned in a school classroom years ago, gathering dust somewhere in the back of your memory. Speed times time equals distance. Think about it like thunder and lightning for a moment. Since that's a version of this idea almost everyone has experienced without realizing it. You see a flash of lightning, and a few seconds later, you hear the rumble of thunder. Sound travels much slower than light, about 1 kilometer every 3 seconds. So, if you count 5 seconds between the flash and the rumble, you know, without needing a ruler or a map, that the lightning struck about 1 2/3 kilometers away. You've just calculated a distance using nothing but a difference in arrival time and a known speed. GPS works on precisely this same principle, just with radio waves instead of sound, and at a level of precision so extreme that ordinary human senses could never begin to notice it. Each satellite in the sky, at every single instant, is broadcasting a very specific signal, and buried inside that signal, along with other information, is an extremely precise timestamp. A note, essentially, saying, "This signal left me at exactly this moment." Your phone, or your car's navigation system, or a hiker's handheld receiver, catches that signal and compares the timestamp buried inside it to its own internal clock, the moment the signal actually arrived. The difference between those two numbers, however microscopically small, tells the receiver exactly how long the signal was traveling. And because the receiver also knows the signal was traveling at the speed of light, it can multiply that tiny sliver of time by that enormous speed, and out comes a distance, the exact distance between the satellite and the receiver. At that precise moment, here's where it gets genuinely delicate, and where you start to appreciate just how extreme the engineering challenge really is. Radio waves, traveling at the speed of light, cover a staggering amount of ground in a very short time. In just 1 millisecond, a thousandth of a second, a signal travels nearly 300 kilometers. In 1 microsecond, a millionth of a second, it still travels 300 meters. That means if your clock, or the satellite's clock, is off by even a tiny fraction of a second, your calculated position can be off by an enormous distance on the ground. A timing error of just 1 millisecond translates into a positioning error of nearly 300 kilometers, not meters, kilometers. So the entire system, from its very first conceptual seed all the way to the phone resting near your pillow tonight, hinges on an almost obsessive demand for precise timing. Everything else, the satellites, the orbits, the receivers, exists in service of one goal: measuring tiny slivers of time with an accuracy that borders on the unbelievable. This is why, when we get further into the story, you'll find engineers becoming almost fanatically preoccupied with clocks. Not ordinary clocks, not even very good mechanical clocks, like the ones John Harrison built centuries ago to solve the longitude problem. We're talking about clocks so precise that they lose or gain less than a single second over hundreds of millions of years. Atomic clocks. We'll spend real time with those soon. But for now, just hold on to this one idea gently, the way you might hold on to a single thought as you drift towards sleep. Position, in this story, is really just disguised time. A satellite doesn't tell you where it is directly. It tells you when it spoke. And from that single whispered timestamp in the unchanging speed of light, distance quietly falls out, almost like a magic trick that isn't a trick at all, just physics, doing exactly what physics always does. One signal gives you one distance from one satellite, and one distance from one satellite tells you that you're somewhere on a sphere surrounding that satellite, but not exactly where on that sphere. To pin down an exact point, you need more than one satellite. You need to hear from several at once and let their overlapping spheres of distance quietly intersect. That idea, called trilateration, is where we're headed next. But first, let's finish the story of transit, the first system ever built to put this principle into practice, and see just how far and how slowly the engineers of the 1960s had to travel before any of this became real. Let's return to the story now, to the 1960s, and to the system that grew directly out of that curious observation about Sputnik's beeping. The system was called Transit, and it was developed by the Johns Hopkins Applied Physics Laboratory, working closely with the U.S. Navy through the early and middle years of the 1960s. It became operational in 1964, and it was, in a very real sense, humanity's first working satellite navigation system. Here's how it worked, at least in its basic shape. A small constellation of satellites, eventually numbering around 6 to 10, orbited the Earth in what's called a polar orbit, meaning they traveled in paths that passed roughly over the north and south poles, rather than around the equator. Each satellite continuously broadcast a radio signal containing information about its own precise orbital position. A ship, most often a Navy submarine that had surfaced briefly, or a surface vessel, would listen for one of these satellites as it passed overhead. As the satellite moved across the sky, the receiver would measure the Doppler shift in its signal, exactly the phenomenon Guerre and Weifenbach had noticed with Sputnik, the way the pitch of the signal rose as the satellite approached and fell as it moved away. By carefully analyzing this shifting pattern over the several minutes it took the satellite to pass overhead, the receiver's onboard computer, and these were genuinely primitive computers by today's standards, could calculate the ship's position with an accuracy of around 200 meters. For its time, this was extraordinary. A ship in the middle of the open ocean, invisible to any landmark, could know its own position to within a couple of city blocks. But transit had real, significant limitations, and it's worth sitting with these limitations for a moment, because every one of them became, quite directly, a problem statement for the engineers who would later build GPS. The first limitation was coverage, because transit satellites orbited fairly low, and there were relatively few of them. Any given point on Earth could typically see one usable satellite pass overhead only once every hour or two. If you needed your position urgently, you might simply have to wait. For a submarine patrolling quietly for weeks, an occasional fix every couple of hours was tolerable. For a fighter jet moving at hundreds of kilometers an hour, it was completely useless. You'd have traveled dozens of kilometers in the time it took to get a single position update. The second limitation was speed sensitivity. The whole system relied on precisely tracking the Doppler shift as the satellite moved relative to the receiver. But if the receiver itself was also moving, a ship pitching in rough seas, or worse, a fast-moving aircraft, that motion corrupted the Doppler measurement, introducing errors that could be difficult to correct. Transit worked best for things that were either stationary or moving slowly and steadily, which ruled out an enormous range of potential uses. The third limitation, and this one will matter enormously in a few parts, was precision. 200 meters was remarkable for open ocean navigation in the 1960s. It was nowhere near good enough for guiding a missile, landing an aircraft in poor visibility, or eventually for the far more ambitious dream that some engineers were already quietly beginning to imagine: letting an ordinary person on the ground know their position down to the width of a room. So even while transit was operational, even while it was actively guiding Navy submarines through the late 1960s and into the 1970s, a small, scattered group of engineers working across different branches of the U.S. military, each somewhat independently, began to sketch out something far more ambitious. A system that wouldn't need you to wait an hour for a single satellite pass. A system that would work continuously, in real time, for objects moving at any speed with a precision measured not in hundreds of meters, but in mere meters. That system didn't have a name yet, and it certainly didn't have a single inventor. In fact, one of the more genuinely interesting parts of this whole story is that it had at least 3 people who could reasonably each claim to be its father, working in different corners of the military establishment, pursuing different approaches, who eventually had to be gently, and not always easily, brought together. Let's meet them now, because understanding who they were and why each of them saw a slightly different piece of the puzzle tells you almost everything about why modern GPS ended up working the way it does. History likes tidy stories with a single inventor, a single light bulb moment, a single name to remember. GPS refuses to cooperate with that impulse, and honestly, that refusal makes it a more interesting story, not a less interesting one. Let's meet the first of our 3 central figures, Roger Easton. Easton worked at the Naval Research Laboratory, and by the late 1960s, he had already spent years thinking carefully about the timing problem we talked about a little earlier, the idea that position is really disguised time. He proposed a concept he called timation, short for time navigation, built around a deceptively simple core idea. Put extremely accurate clocks into orbit and let ground receivers calculate their position purely by measuring the time delay of signals from those clocks. Exactly the principle we walked through together a short while ago. Easton was, by most accounts, a quiet, methodical engineer, deeply preoccupied with precision timekeeping rather than with the flashier aspects of satellite design. He experimented with early atomic clocks in orbit, and he championed an idea that would become absolutely central to the final system: that satellites should carry the most accurate clocks technology could offer, and that the entire navigation system should be built around timing, first and foremost. History has gradually come to credit him as one of the true fathers of GPS, though for much of his career, recognition came slowly and quietly, the way it often does for people more interested in solving problems than in claiming credit for them. The second figure is Ivan Getting, a physicist who had earlier worked on radar systems during the Second World War and later became the founding president of the Aerospace Corporation, a nonprofit deeply embedded in the Air Force's space programs. Getting approached the problem from a different angle than Easton. Where Easton was fixated on timing and clocks, Getting was thinking in terms of a complete unified system: satellites, receivers, orbits, all engineered together to serve military users, particularly for guiding aircraft and missiles with real-time, continuous accuracy. Something transit's occasional Doppler fixes simply couldn't provide. Getting pushed hard through the 1960s for a comprehensive satellite-based navigation system for the Air Force. And he's often remembered as the person who articulated the big picture vision, the architecture, the case for why the military needed something far more capable than what transit or timation alone could offer. The third figure, and in many ways the person most responsible for actually pulling everything together into what became the real operational GPS, is Bradford Parkinson, an Air Force colonel and engineer. In the early 1970s, Parkinson was placed in charge of a fractured, somewhat chaotic collection of overlapping satellite navigation efforts scattered across different branches of the military, each with its own preferred approach, each somewhat territorial about its own ideas. Parkinson's genuine achievement wasn't a single brilliant technical insight, so much as an act of synthesis, gathering the best ideas from Timation's obsession with precise clocks, from Transit's practical orbital experience, and from various Air Force proposals for continuous real-time positioning, and welding them together into one coherent design. There's a well-known story from this period, possibly a little embellished, with retelling over the decades the way these stories often are, that Parkinson and a small group of colleagues sketched out the core architecture of what would become GPS over a single intense weekend at the Pentagon in 1973, hammering out decisions about orbital altitude, the number of satellites needed, and the fundamental signal structure that would let receivers on the ground calculate their position. Whether it truly happened in one dramatic weekend or was pieced together more gradually over subsequent months hardly matters for our purposes tonight. What matters is that by the end of that period, the essential shape of GPS as we know it had been decided. 24 satellites, later refined slightly, arranged in 6 distinct orbital planes, positioned at a carefully chosen altitude of just over 20,000 kilometers. high enough to give each satellite a wide view of the Earth below, allowing a receiver anywhere on the planet's surface to see multiple satellites simultaneously at nearly any moment, day or night. The program was formally christened Navstar GPS in 1973, and the first prototype satellites, still experimental, still carrying the scars of trial and error, began launching later that decade. It's worth noticing something quietly moving in this part of the story, something we saw echoed in the tale of the quantum physicists too, if you think back to other nights of listening to stories like this one. Great inventions rarely spring from a single mind working in isolation. They emerge from friction, from several people circling the same problem with different instincts, different specialties, sometimes even mild rivalry, until eventually their separate insights are forced, often by circumstance rather than harmony, into a single working design. Easton gave GPS its obsession with precise time. Getting gave it its ambition, its case for a complete, unified system. Parkinson gave it the discipline to actually become real, actually get built, actually get launched into orbit. And what they built together at its very core rests on one elegant piece of geometry, an idea nearly as old as mathematics itself, repurposed for the space age. It's called trilateration, and it's where we're headed next. Let's slow right down again, because this next idea is the true geometric heart of GPS. And once it settles into your mind, the little blue dot on your phone's map will never look quite the same way again. Imagine for a moment that you're standing somewhere on a large, dark field at night, completely lost, with no landmarks in sight. Somewhere out there, hidden in the darkness, is a friend of yours, and this friend calls out to you. You can't see them, but you can hear the sound of their voice, and by timing exactly how long it takes the sound to reach you, and knowing the speed of sound, you calculate that they're exactly 100 meters away from you. That single piece of information is useful, but it's not enough to know exactly where they are. All it tells you is that your friend is standing somewhere along the edge of an enormous circle, 100 meters in radius, centered on you. They could be due north of you, or due south, or anywhere along that entire ring. One distance measurement narrows things down, but it doesn't pin down a single point. Now imagine a second friend also calls out from a different location, and you calculate that they're exactly 80 meters away from you. Now you have two circles, two possible rings where each friend could be standing. But here's the elegant part. Two circles, unless they're positioned in an unusual way, generally intersect at exactly 2 points. So now your combined information has narrowed the possibilities down from anywhere on an infinite ring to just 2 specific spots in the entire field. Add a third friend, calling from yet another position, and a third circle appears. And that third circle, more often than not, only passes through one of those 2 remaining points, not both. The moment you have 3 distance measurements from 3 known locations, the intersection collapses down to a single, unique point. You now know, with real confidence, exactly where you are standing on that dark field. This is trilateration, and it's genuinely one of the oldest tricks in the geometric toolbox, far older than satellites, far older than radio. Surveyors have used versions of this idea for centuries to map land. It shows up in earthquake science, where seismologists use the arrival time of shock waves at different monitoring stations to pinpoint an earthquake's epicenter. It's a strikingly simple, strikingly powerful idea, and GPS is, at its heart, just this same idea. translated into 3 dimensions and stretched across the sky. Here's how it scales up. Instead of friends calling across a dark field, you have satellites high above the Earth, each one broadcasting its own precise position and the exact moment its signal was sent. Your receiver, listening on the ground, measures how long each signal took to arrive, and using the speed of light, converts that travel time into a distance, exactly as we discussed a couple of parts ago. Each of those distances defines not a circle this time, but a sphere, a 3-dimensional bubble surrounding the satellite, with a radius equal to the calculated distance. You could be anywhere on the surface of that sphere. With a second satellite's distance, a second sphere appears, and where 2 spheres intersect, you don't get a single point, you get a circle, floating somewhere in 3-dimensional space, tracing out every possible location that satisfies both distance measurements at once. A third satellite sphere intersects that circle at, generally, exactly 2 points. 2 candidate locations remain, one of which, in almost every real-world situation, is obviously wrong, floating somewhere absurd like deep underground or far out in space, easily discarded. The other point is your actual location. So in principle, in a perfectly clean and idealized world, 3 satellites should be all you ever need. 3 distances, 3 spheres, 1 sensible intersection point, and you'd know exactly where you are, anywhere on Earth, at any moment. And for a long time, this is genuinely how the early engineers imagined the system would work. 3 satellites in view, 3 careful distance measurements, and a clean geometric answer. But there's a catch hiding inside this beautiful picture, a catch that took real, hard-won engineering insight to solve properly. And it comes back, once again, to that theme we touched on earlier: clocks. Specifically, the fact that the clock inside your receiver, inside your phone, inside your car, is nowhere near as accurate as the clocks riding aboard those satellites. And that single imperfection, that one small, humble limitation, is exactly why you don't actually need 3 satellites to find your position. You need 4. Let's pick up exactly where we left off, with that quiet little catch hiding inside the elegant picture of 3 intersecting spheres. Remember, from a couple of parts back, just how unforgiving this system is about timing. A clock error of a single millisecond translates into a positioning error of nearly 300 kilometers. That's not a small mistake. That's the difference between knowing you're in one city and thinking you're in an entirely different one, several hundred kilometers away. The satellites themselves solve their side of this problem with extraordinary care. Each one carries multiple atomic clocks on board, instruments so precise they'll only drift by roughly 1 second over tens of thousands of years. And we're going to spend real time appreciating just how remarkable that is in the next part of our story. But your receiver, the little chip inside your phone, cannot carry an atomic clock. Atomic clocks, even miniaturized ones used in specialized equipment, are still relatively bulky, expensive, and power-hungry, entirely impractical for a consumer device you carry in your pocket and expect to last a full day on a single charge. So instead, your phone relies on a cheap, ordinary quartz crystal oscillator, the same basic kind of timekeeping component found in an inexpensive wristwatch. A quartz oscillator is a perfectly fine timekeeper for telling you it's roughly 11:30 at night. It is a catastrophically bad timekeeper for the kind of precision GPS demands. A typical quartz clock might drift by a fraction of a second over the course of just a single day, an error that, translated through the speed of light, would produce a positioning error of hundreds of thousands of kilometers, genuinely useless for navigation. So here's the puzzle the engineers faced. The satellites know the time with exquisite atomic precision. The receiver's clock is comparatively a mess, drifting unpredictably, unreliable by orders of magnitude. How can the whole system possibly work if one half of the equation, your own local clock, simply cannot be trusted? The elegant solution, and this is genuinely one of the more beautiful pieces of engineering hiding inside GPS, is to stop treating the receiver's clock error as something that needs to be eliminated and instead treat it as simply one more unknown quantity to be solved for right alongside your position. Think back to the trilateration problem. With 3 satellites, we were solving for 3 unknowns, your position along 3 dimensions. Let's call them your location's north-south coordinate, its east-west coordinate, and its up-down altitude. 3 unknowns, 3 equations from 3 satellite distances, and the geometry resolves cleanly to a single point, provided every distance measurement is perfectly accurate. But if your receiver's clock is off by some unknown amount, then every single distance measurement you calculate is subtly wrong, shifted by exactly that same clock error in exactly the same direction, because that same faulty clock was used to time every single signal's arrival. It's a consistent, shared error, not a random one, and that consistency turns out to be exactly what makes it solvable. The engineers simply added a 4th unknown to the math, the receiver's clock error itself, alongside the 3 position unknowns. 4 unknowns now require 4 independent equations to solve cleanly, and 4 equations require 4 separate distance measurements, which means 4 separate satellites. Here's the genuinely elegant part. When the receiver has signals from 4 satellites instead of 3, it can solve all 4 unknowns simultaneously, your 3-dimensional position and its own clock error, all at once, through a bit of careful mathematics happening silently inside the chip. And once it knows its own clock error, it can actually correct for it, syncing its cheap quartz clock to within a few billionths of a second of the atomic time being broadcast from space. Your phone, in effect, briefly borrows the precision of an atomic clock every single time it calculates a position fix, entirely for free, using nothing more than an extra satellite signal and some clever algebra. This is why, if you've ever glanced at a GPS app showing satellite signal strength, you'll notice it typically wants to see at least 4 satellites before it reports a confident position, and often shows more, sometimes 8, 10, or more when visible, using the extra signals to refine accuracy even further and cross-check for errors. It's a wonderfully humble piece of design when you sit with it for a moment. Rather than demanding an expensive, precise clock inside every single receiver on Earth, every phone, every car, every hiking device, the entire system was built to gracefully absorb the imprecision of cheap, ordinary clocks, simply by asking one small favor of the sky. 1 extra satellite, please, and I'll figure the rest out myself. Now, all of this cleverness with the receiver's cheap clock only works because the satellites themselves hold up their end of the bargain with an almost obsessive, extraordinary precision. And that obsession, that relentless pursuit of the perfect clock, is itself an entire story, stretching back decades before the first GPS satellite ever reached orbit. Let's turn to that story now, gently, the way you might turn over in bed toward a more comfortable position, and meet the strange, ticking heart of the entire system. The atomic clock. Every clock humanity has ever built, going all the way back to sundials and water clocks and candle clocks, works on the same basic principle. Find something that repeats at a steady, predictable rate and count the repetitions. A pendulum swings back and forth at a steady rate, and you count the swings. A quartz crystal, when you run a tiny electric current through it, vibrates at a steady rate, many thousands of times per second, and you count the vibrations. The better and more stable the thing you're counting, the more accurate your clock becomes. For most of human history, the best available steady repeating thing was mechanical. A pendulum, a balance wheel, a vibrating crystal, and all of these, however carefully engineered, are subtly at the mercy of the physical world around them. Temperature changes the length of a pendulum ever so slightly. Humidity, air pressure, even the gentle pull of the moon can nudge a mechanical timekeeper off its steady rhythm, accumulating tiny errors that add up over days and years into real, meaningful drift. Scientists in the mid-20th century began to wonder if there was something in nature more perfectly steady than any spring or pendulum could ever be. And they found their answer, rather beautifully, inside the atom itself. Here's the core idea, and we'll keep it gentle and conceptual rather than technical. Every atom of a given element is, in a very real sense, identical to every other atom of that same element anywhere in the universe. A cesium atom here on Earth tonight is, for all practical purposes, physically indistinguishable from a cesium atom on the far side of the galaxy, and electrons within an atom can absorb or release very precise, very specific amounts of energy as they jump between certain allowed states, releasing or absorbing a signal at an extraordinarily exact, unchanging frequency, a frequency dictated by the fundamental laws of physics rather than by any humanly manufactured spring or crystal. Scientists realized that if you could reliably trigger and count these atomic transitions, you'd have access to a tick more perfectly steady than anything humans had ever built by hand, a tick anchored not to engineering, but to the unchanging structure of the atom itself. The cesium atom turned out to be an especially convenient choice for this purpose, and in 1967, an international body of scientists made a genuinely remarkable decision. They redefined the second itself, the fundamental unit of time, no longer in terms of the Earth's rotation or its orbit around the Sun, both of which turn out to be surprisingly, if very slightly, irregular, but in terms of the cesium atom. 1 second was now officially defined as the time it takes for a cesium atom to complete exactly 9,192,631,770 of these particular energy transitions. Sit with that number for a moment. Over 9 billion oscillations, every single second, ticking away with a regularity so extreme that a well-built cesium atomic clock will drift by less than 1 second over the course of tens of thousands, sometimes even millions, of years. These clocks are precisely what fly aboard every GPS satellite. Each satellite typically carries several atomic clocks on board, usually cesium, or the closely related rubidium variety, along with backup units in case one fails. Because remember, an error of even a few billionths of a second in these clocks translates directly into a positioning error on the ground of meters or more. There's something quietly poetic about this, if you let yourself sit with it for a moment tonight. The device that lets you find your way home, that guides an ambulance through unfamiliar streets, that helps a hiker locate themselves on a foggy mountainside. ultimately depends on humanity's ability to listen extraordinarily closely to the inner rhythm of a single atom, a rhythm smaller and more delicate than almost anything else in the physical world, yet more reliable and unwavering than anything else we've ever managed to build. But here's where the story takes its strangest turn yet. A turn that even the engineers who built the very first GPS satellites weren't entirely certain how to handle, and one that reaches all the way back to a patent clerk in Switzerland and a quiet, careful physicist in Germany, both of whom we've met before in an entirely different story, on an entirely different night, because it turns out that even a perfect atomic clock ticking away with unimaginable steadiness doesn't tick at quite the same rate everywhere in the universe. Up in orbit, moving at tremendous speed, sitting in a weaker gravitational field than we experience down here on the surface, those atomic clocks tick just slightly differently than an identical clock resting quietly on a shelf in a laboratory on Earth. Not because anything is wrong with the clocks, because the universe itself, according to Einstein, simply doesn't let time flow at the same rate everywhere. We'll get to that in a little while, and it's a genuinely beautiful piece of the story, a moment where abstract, seemingly untestable, theoretical physics from over a century ago turns out to be something engineers had to account for, quite literally, or GPS would drift wildly off course within a single day. But for now, just rest here for a moment with the atomic clock itself. 9,200,000,000 and some million oscillations every second inside a small metal box orbiting quietly above you right now, more patient and more precise than anything else humans have ever managed to build, keeping faithful, steady time so that you, wherever you happen to be tonight, can always, quietly, know exactly where you are. Let's pick the thread back up gently, right where we left it. An atomic clock ticking away aboard a satellite, more precise than almost anything else humans have ever built. And yet, we said, something strange happens to that clock once it's up there in orbit. It doesn't quite keep the same time as an identical clock resting on a shelf back on Earth. To understand why, we need to meet once again a name you may remember from other quiet nights of stories like this one. Albert Einstein, back in 1905, in that same extraordinary year we've spoken of before, the year a young patent clerk in Switzerland published 4 papers that would each reshape physics on their own. Einstein introduced an idea called special relativity, and buried inside that theory is a conclusion so strange that even now, over a century later, it still resists easy intuition. Time, Einstein argued, is not the same for everyone. It doesn't tick at a universal, fixed rate that everyone in the universe shares. Instead, how fast time passes for you depends, among other things, on how fast you're moving relative to someone else. Here's the core idea, stripped down to its gentlest form. The faster an object moves relative to an observer, the slower time passes for that object from the observer's point of view. Not because anything is broken, not because the clock is faulty. Time itself, according to Einstein, genuinely runs at a different rate. This effect, called time dilation, is utterly imperceptible at the speeds we experience in ordinary life. Walking, driving a car, even flying in a commercial jet, these speeds are so tiny compared to the speed of light that the time dilation they produce is smaller than any clock could ever hope to measure. Which is exactly why nobody noticed this effect. Nobody even suspected it for the entire history of human civilization, up until Einstein worked it out on paper using nothing but careful reasoning and a deep respect for the constancy of the speed of light. But GPS satellites are not moving at ordinary speeds. They orbit the Earth at roughly 14,000 kilometers per hour, nearly 4 kilometers every single second. That's still nowhere close to the speed of light, but it's fast enough, and GPS demands such extreme precision that the tiny sliver of time dilation this produces becomes not just measurable, but genuinely important. Here's the actual number, and it's worth sitting with it for a moment, because of how small and how consequential it is at the same time. Due to their orbital speed alone, the clocks aboard GPS satellites run slower than identical clocks on the ground by about 7 microseconds every single day. 7 millionths of a second. That sounds almost comically tiny, doesn't it? 7 millionths of a second seems like nothing at all. The kind of number that surely couldn't matter to anyone. But remember what we learned a little earlier tonight, that a timing error of just 1 millisecond translates into a positioning error of nearly 300 kilometers. 7 microseconds left uncorrected would translate into a positioning error of a couple of kilometers every single day, and that error would simply keep accumulating day after day, growing larger and larger until the whole system became useless within a matter of hours. This is worth pausing on, gently, because it's one of the more quietly remarkable moments in this entire story. Special relativity, when Einstein first proposed it, was an almost purely theoretical idea. There was no everyday technology in 1905 that needed it. No clock precise enough, no situation ordinary enough to actually reveal its effects in daily life. For decades, it remained something tested mostly through careful physics experiments, particle accelerators, astronomical observations, elegant but essentially academic confirmations of a beautiful theory. And then, roughly 7 decades later, engineers building a navigation system for submarines and aircraft discovered they could not make their system work correctly without explicitly accounting for it. A theory born from pure thought about light and motion turned out to be load-bearing infrastructure for an ordinary person's phone, quietly correcting itself every second of every day, so that when you check a map app to find the nearest late-night pharmacy, the numbers come out right. There's something worth carrying with you into sleep tonight in that fact alone, that the strangest, most abstract ideas in physics, the ones that once seemed like philosophical curiosities with no bearing on daily life, have this quiet habit of turning out to matter enormously, often decades later, in ways nobody could have predicted at the time. But here's the twist, and it's the twist that makes this part of the story genuinely delightful, rather than simply neat. Special relativity is not the only relativistic effect at play up there in orbit. There's a second effect, working in the exact opposite direction, and it comes from an entirely different piece of Einstein's thinking, one he wouldn't fully develop until a full decade after his miracle year. A theory about gravity itself, and about how gravity too bends the flow of time. That effect turns out to be even larger than the one we just discussed, and it points the other way entirely. Let's turn to it now and finish the relativity story properly, because it's here that the whole picture snaps into focus. A decade after special relativity, in 1915, Einstein published a far more ambitious theory, one that had taken him years of grinding, often frustrating work to complete. General relativity, where special relativity dealt with speed and motion, general relativity dealt with something even stranger, gravity itself. Einstein's radical proposal was that gravity isn't really a force pulling objects toward each other in the way Newton had imagined it for over 2 centuries. Instead, massive objects, like the Earth, gently curve the fabric of space and time around themselves, and what we experience as gravity is really just objects following the natural curves in that warped fabric. And one of the consequences of this curving is, once again, about time. According to general relativity, time runs slightly slower the closer you are to a massive object. The deeper you sit within its gravitational field, and it runs slightly faster the farther away you move from that same massive object, out where gravity's grip weakens. This might sound abstract, but it has been tested and confirmed with real precision many times over. Extremely sensitive atomic clocks placed at different altitudes here on Earth, even just a few floors apart in the same building, have been shown to tick at very slightly different rates. The ones higher up, farther from the Earth's mass, ticking just a touch faster than the ones lower down. Now think about where the GPS satellites are sitting. Not down here on the surface, deep within Earth's gravitational field, but roughly 20,000 kilometers up, far above us, in a noticeably weaker region of that same gravitational field. According to general relativity, that means the clocks aboard the satellites should run faster than identical clocks down here on the ground, simply because they're sitting in weaker gravity. And when engineers calculated exactly how much faster, they found a number considerably larger than the special relativity effect we just discussed. About 45 microseconds per day, the satellite clocks running fast due to gravity alone. So now we have 2 competing effects pulling in opposite directions. Special relativity, caused by the satellite's orbital speed, makes its clock run about 7 microseconds slower each day. General relativity, caused by its distance from Earth's gravity, makes that same clock run about 45 microseconds faster each day. Combine them together, and the net effect is that GPS satellite clocks run faster than clocks on the ground by roughly 38 microseconds every single day. Not a huge number in absolute terms, but remember, once again, our earlier lesson about just how unforgiving this system is. 38 microseconds of uncorrected drift left to accumulate would translate into a positioning error that grows by roughly 10 kilometers every single day. Within a week, the entire GPS system would become completely, hopelessly useless. Every position it reported wildly, uselessly wrong. Here's the part of this story that always feels, at least to me, quietly beautiful. The kind of thing worth turning over gently in your mind as you drift towards sleep. The engineers who built GPS in the 1970s knew about this problem. Before the first satellites ever launched, they knew, from theory alone, exactly how much correction each satellite clock would need. And so, before launch, engineers deliberately adjusted the frequency of each satellite's atomic clock, tuning it to tick very slightly slower than a normal, correct atomic clock would, so that once the satellite reached orbit and the combined relativistic effects sped it back up, it would end up ticking at exactly the right rate to match clocks on the ground. They pre-corrected for a century-old theoretical prediction made by a man scribbling equations by hand long before anyone imagined satellites, spaceflight, or a global positioning system existed at all. And it worked. It still works. Right now, tonight, as satellites pass quietly overhead, there's a wonderful, almost mischievous detail buried in this story too. In the earliest GPS satellites, engineers actually built in a switch, allowing the relativistic correction to be turned on or off, largely as a hedge against the possibility that the theory might somehow be wrong, or that some other unaccounted factor might throw the calculations off. Once real data came back from orbit. When the first satellite reached orbit, and its clock was compared against ground clocks, the drift matched Einstein's prediction so precisely that the correction was switched on permanently, and it has remained on in every GPS satellite ever launched since. Sit with that for a moment. A theory born from pure thought about falling elevators and curved space, tested not in some grand experiment, but quietly, permanently, inside every single satellite, silently keeping watch above your bedroom right now. Every time your phone finds your position tonight, somewhere in that calculation, a tiny correction is being applied, a correction that exists because 110 years ago, a physicist in Berlin worked out how gravity bends time itself. We're going to leave relativity behind now, gently, and return to the more grounded, practical side of the story, because knowing how the clocks work and how they're corrected is only half the picture. The other half is the enormous physical undertaking of actually building, launching, and arranging an entire constellation of these satellites around the Earth, a project that stretched across more than a decade and very nearly didn't happen at all. By the mid-1970s, the design existed on paper. 24 satellites arranged carefully in 6 distinct orbital planes, tilted at 55 degrees relative to the equator, circling the Earth at an altitude of a little over 20,000 kilometers, each satellite completing a full orbit roughly twice every day. But a design on paper is a very different thing from a working system in space. And the journey from blueprint to fully operational constellation took the better part of 2 decades, stretched across the 1970s, the 1980s, and into the early 1990s, marked by technical struggles, funding battles, and at least one genuine near cancellation. The very first satellite, a prototype known as Navigation Technology Satellite 2, launched in 1977, essentially a continuation of Roger Easton's earlier Timation work we spoke about a few parts back, carrying atomic clocks into orbit to prove the fundamental timing concept could actually work in practice, not just in theory. The first true GPS satellites, part of what's called Block I, began launching in 1978 from Vandenberg Air Force Base in California. These were experimental, developmental satellites built to validate the system's core design before committing to the full 24-satellite constellation. Over the following 6 years, engineers launched a series of these Block I satellites, learning, adjusting, occasionally watching a launch fail outright, the way early space programs so often do, and slowly refining both the satellites themselves and the ground systems needed to control them. Then, in January 1986, disaster struck the entire American space program at once, though not directly related to GPS. The Space Shuttle Challenger broke apart shortly after launch, a tragedy that killed all 7 crew members aboard, and, among its many far-reaching consequences, grounded the Space Shuttle fleet for nearly 3 years. This mattered enormously for GPS because at the time, the shuttle had been designated as the primary vehicle for launching the newer generation of GPS satellites into orbit. With the shuttle grounded, the entire GPS deployment schedule ground to a halt, forcing planners to pivot back to traditional expendable rockets instead, a shift that cost precious time the program could ill afford. Meanwhile, funding for the program was never entirely secure. GPS was, throughout this period, fundamentally a military project, developed and paid for by the U.S. Department of Defense, and like many expensive, long-term military programs, it periodically faced skepticism from budget planners who questioned whether the enormous cost was truly justified. More than once during the late 1970s and early 1980s, the program's scope was scaled back, its full 24-satellite vision temporarily reduced to smaller, cheaper configurations before political and military momentum eventually restored the original ambition. There's a particular moment in this story worth pausing on because it reveals something important about why GPS eventually became available to ordinary civilians at all, rather than remaining a purely classified military tool. In September 1983, a Korean Airlines passenger flight, Flight 007, accidentally strayed into restricted Soviet airspace due to a navigational error and was shot down by a Soviet fighter jet, killing all 269 people aboard. The tragedy prompted an outraged international response, and in its aftermath, President Ronald Reagan issued a directive stating that once GPS became fully operational, its signals would be made available for civilian use worldwide, free of charge, specifically so that navigational tragedies of this kind could be prevented in the future. This decision, made in the wake of genuine human loss, quietly planted the seed for everything that would later grow from GPS beyond its original military purpose. Though, as we'll see in a few parts, the civilian signal that was actually provided for the next 17 years came with a very deliberate catch. Through the late 1980s, launches continued steadily, gradually filling out the constellation. Satellite by satellite, orbital plane by orbital plane, the sky slowly filled with these quiet, whispering machines, each one carrying its precisely tuned atomic clocks, each one broadcasting its endless, patient signal down toward the Earth below. Finally, on April 27, 1995, the U.S. Air Force formally declared GPS to have reached what's called full operational capability. 24 satellites, properly spaced across 6 orbital planes, providing continuous, worldwide coverage, meaning that from virtually any point on Earth's surface, at virtually any moment, at least 4 satellites would always be visible above the horizon, exactly the minimum needed, as we discussed a few parts ago, to solve for both position and that stubborn receiver clock error simultaneously. It had taken roughly 2 decades from Bradford Parkinson's pivotal Pentagon planning sessions in the early 1970s to this final declaration in 1995. 2 decades of launches and failures, funding fights and tragedies, careful engineering and quiet persistence, to build something that today most people never think about at all, glancing down at a small glowing dot on a screen without a single thought for the constellation of atomic clocks patiently circling overhead to put it there. Now that the satellites were finally up there, fully arranged and broadcasting, it's worth slowing down and looking closely at exactly what they're saying, because the actual structure of a GPS signal, the whispered message each satellite sends down through the dark, turns out to be a small masterpiece of engineering in its own right, and that's where we're headed next. Let's slow down now and look closely at the actual whisper. The signal each satellite sends endlessly toward the Earth, day and night, whether or not anyone below happens to be listening. Each GPS satellite broadcasts on very specific radio frequencies, gentle, faint transmissions that carry two main kinds of information woven together. First, a timestamp generated by that satellite's onboard atomic clock, marking the precise moment the signal was sent. Exactly the piece of information we discussed a while back. The one that lets a receiver calculate distance using the speed of light. Second, a set of data describing the satellite's own precise orbital position at that moment. Information called ephemeris data. Essentially, the satellite quietly announcing, moment to moment, exactly where in the sky it currently is. But here's a genuinely elegant piece of the puzzle we haven't touched yet. There are, at any given moment, roughly 30 operational GPS satellites in orbit, all broadcasting on very similar frequencies, all sending their signals down toward the same general region of sky, toward the same receiver sitting quietly in your pocket or on your dashboard. How does your receiver possibly untangle which whisper came from which satellite when they're all arriving at almost the same faint volume, on almost the same frequency, all at once? The answer lies in a clever mathematical trick called a pseudo-random code, sometimes described more casually as a spread spectrum signal. Each satellite is assigned its own unique, seemingly random sequence of ones and zeros, a kind of digital fingerprint, repeating over and over in its broadcast. The sequence looks like random noise to anyone who doesn't already know the pattern, but it's not actually random at all. It's carefully, mathematically generated, and your receiver has all 30 of these unique patterns already stored inside it. When your receiver picks up the tangled mess of overlapping satellite signals, it compares what it's hearing against each known pattern, one at a time, sliding the pattern back and forth in time until it finds a strong match, a moment where the pattern it's looking for lines up almost perfectly with a piece of the incoming noise. Once it finds that match, it has effectively pulled one single satellite's signal cleanly out of the tangled chorus of all the others. The way your ear might learn to pick out one particular voice, speaking your name in a crowded, noisy room. Once you know exactly what that voice sounds like, this same clever trick also solves another problem, quietly hiding in the background. Because the pattern is so specific and distinctive, your receiver can detect an extraordinarily faint signal, weaker even than the background radio noise of the universe itself, buried well beneath what most receivers could ever hope to notice directly. This is part of why GPS signals, which travel over 20,000 kilometers, and arrive at your phone weaker than almost any other radio signal you'll ever receive, can still be picked out reliably, even by a small, inexpensive antenna tucked inside a slim smartphone. There's something worth appreciating here, gently, about the sheer faintness of what we're talking about. By the time a GPS signal has traveled all that distance from satellite to receiver, it has weakened enormously to a level so low that without this pseudo-random trick, it would be genuinely difficult to distinguish from the ordinary background hiss of the universe. The same faint static a radio telescope picks up from the leftover glow of the Big Bang itself. And yet, buried inside that near silence, a perfectly ordinary phone manages to extract enough information to know its own location down to a few meters. It's a small daily miracle, one that almost nobody ever notices, precisely because it works so quietly and so well. Once the receiver has cleanly separated the signal from each visible satellite, it reads the timestamp, reads the ephemeris data, describing that satellite's position, and repeats the whole careful process for at least 3 and usually 4 or more satellites simultaneously. From there, the trilateration math we discussed a few parts back, and the clock correction trick that followed it, quietly does the rest, converting a handful of overlapping whispers from space into a single, confident dot on a map. All of this, remarkably, happens continuously, dozens of times per second, silently refining and updating your position as you move. Whether you're walking down a street, driving along a highway, or simply lying still in bed while your phone, out of habit more than necessity, keeps a faint, patient watch on where you are. But not every part of this system was always this open and freely available to ordinary people. For nearly 2 decades after the constellation first became operational, the signal that reached civilian receivers, ordinary people's cars, boats, and eventually phones, was deliberately, secretly degraded, blurred just enough to keep its full precision reserved for military use alone. That story of secrecy, strategy, and an eventual change of heart is where we're headed next. Remember, from a couple of parts back, President Reagan's directive that GPS signals would eventually be made available to civilians worldwide, free of charge, following the tragic shooting down of Korean Airlines Flight 007 in 1983. That promise was real, and it was in fact kept. But it came with a quiet, deliberate asterisk attached to it, one that most ordinary users of early GPS devices never fully understood, and one that shaped the civilian experience of GPS for nearly 2 full decades. The concern, from the military's perspective, was straightforward, if a little uncomfortable. GPS had been built, first and foremost, as a military tool, designed to guide missiles, aircraft, and ships with extraordinary precision. If that same extraordinary precision, accurate to within a few meters, were made freely available to absolutely anyone on Earth, that would include, quite plainly, potential adversaries of the United States. A hostile nation, or even a non-state actor, could in principle use civilian GPS receivers to guide their own weapons with a level of accuracy the U.S. military had spent enormous resources developing exclusively for itself. So the engineers built in a safeguard, a deliberate feature called selective availability, often shortened simply to SA. The idea was elegantly simple, if quietly frustrating for civilian users. The satellites would broadcast 2 separate signals. One, called the Precise Positioning Service, carried the full, unmodified accuracy of the system, but was encrypted, accessible only to military receivers equipped with the proper cryptographic keys. The other, called the Standard Positioning Service, was freely broadcast to anyone with an ordinary civilian receiver, but its timing information was deliberately, artificially corrupted, introducing a controlled, randomly shifting error into the signal. This intentional corruption degraded civilian accuracy from the system's natural few-meter precision down to something considerably worse, typically somewhere between 50 and 100 meters of uncertainty. Good enough, the reasoning went, for a hiker to find the general direction of a trailhead or a boat to confirm. It was somewhere in the right general stretch of coastline, but nowhere near precise enough to guide a weapon toward a specific building or a specific target. For anyone who used civilian GPS receivers during the 1990s, this degraded accuracy was simply the reality of the technology. Early handheld GPS units and the first GPS-equipped cars would happily report your position, but that little dot on the map might genuinely be sitting on the wrong street or in a neighboring field, and there was no way around it. Short of possessing military-grade equipment, you almost certainly didn't have access to. There was, interestingly, a partial workaround that some civilian users discovered and employed, called differential GPS. Since the artificial error introduced by selective availability affected an entire region roughly equally at any given moment, a fixed, precisely surveyed ground station, one whose exact location was already known with certainty, could compare its own GPS reported position against its actual known position, calculate exactly how much error was currently being introduced, and broadcast a correction signal to nearby receivers, letting them subtract that error back out. This technique became genuinely important for applications like maritime navigation near harbors and surveying, where even the degraded civilian signal simply wasn't good enough on its own. Selective availability remained active throughout the 1990s, a quiet compromise between military caution and the promise of civilian access, and it shaped an entire generation's early experience of what GPS technology could and couldn't do. If you ever used one of those first bulky handheld GPS units on a hiking trip, or watched an early in-car navigation system confidently place your vehicle in the wrong lane, or occasionally in an entirely different street altogether, you were experiencing selective availability at work, a deliberately blurred picture of the truth. Blurred not by any limitation of physics, but by policy, by a careful, considered decision about who was allowed to see how clearly. But policy, unlike physics, can change. And in the closing months of the year 2000, it did, in a decision that arrived somewhat abruptly, and that quietly transformed GPS from a useful but limited civilian tool into the foundation of an entirely new kind of everyday technology, the beginning of the world we now live in, one where a small glowing dot on a phone screen can guide you with startling precision to almost anywhere you might want to go. Let's turn to that moment now, because it's genuinely one of the pivotal turning points in this whole story. The moment GPS quietly became something close to what it is tonight. By the late 1990s, a quiet shift had begun taking place inside the U.S. military and political establishment, a gradual reconsideration of whether selective availability was still serving its intended purpose, or whether, increasingly, it was simply holding back an enormously valuable civilian and commercial technology for a security benefit that was becoming harder and harder to justify. Part of what changed the calculation was a genuinely clever piece of engineering that had emerged in the civilian world during the 1990s, largely in response to selective availability itself. Remember the differential GPS technique we just discussed, using known, fixed reference stations to calculate and broadcast correction signals. As this technique matured and spread, particularly through private companies and civilian government agencies, building out networks of these reference stations, it became possible for a sufficiently motivated civilian user to correct for most of the selective availability error anyway, achieving accuracy nearly as good as the restricted military signal, just through clever workarounds on the receiving end. This created an uncomfortable realization within the Department of Defense. Selective availability was, by the late 1990s, increasingly inconveniencing millions of ordinary civilian users and legitimate commercial applications. Things like aviation, agriculture, and emergency services, while providing a shrinking and arguably illusory security benefit against any adversary, determined and resourceful enough to build their own differential correction network. There was also quietly a growing economic argument. American companies had begun building an entire industry around GPS-enabled devices, and it was becoming increasingly clear that removing selective availability could unlock enormous economic and technological growth, strengthening America's position as the leading provider of a technology the rest of the world was going to want and would otherwise potentially develop rival alternatives to. On May 1st, 2000, President Bill Clinton announced that selective availability would be turned off, effective immediately that very night. The announcement caught many people somewhat by surprise, arriving with less fanfare than you might expect for a decision that would ripple outward into nearly every corner of daily life over the following 2 decades. The technical change itself was almost anticlimactic in its simplicity. Engineers at the satellite control facilities simply stopped introducing the deliberate timing error into the civilian signal. No new satellites needed to be launched. No new equipment was required on the ground. The system's underlying natural accuracy, the same few-meter precision the military signal had enjoyed all along, was simply, suddenly, made available to absolutely anyone with an ordinary civilian GPS receiver anywhere in the world at no cost. The improvement was immediate and dramatic. Overnight, civilian GPS accuracy improved roughly tenfold, from that frustrating 50 to 100-meter uncertainty down to somewhere in the range of 10 meters or better, a level of precision suddenly good enough for genuinely serious, practical applications that had simply been impossible before. It's worth sitting with just how much changed because of this single administrative decision, made not because of any new invention or scientific breakthrough, but simply because policy finally caught up with what the technology had been quietly capable of all along. Within just a few years of selective availability being switched off, GPS chips began shrinking rapidly in size and cost, cheap enough and small enough to be embedded into consumer electronics that would have seemed like science fiction a decade earlier. In-car navigation systems, once expensive, clunky add-ons of questionable reliability, suddenly became genuinely trustworthy tools, precise enough to guide a driver confidently onto the correct exit ramp rather than merely the correct general highway. And then, starting in the mid-2000s, GPS chips began appearing inside an entirely new category of device, the smartphone, transforming what had been a niche navigational tool into something almost every person on Earth would eventually carry in their pocket, checked dozens of times a day. Without a second thought, think, for a moment, about everything that quietly grew out of this one decision. Ride-sharing apps that can find you on an unfamiliar street corner within seconds. Delivery services that can track a package or a meal moving steadily toward your front door in real time. Fitness apps that can map the exact route of your evening run down to the meter. Emergency services that can locate a caller in distress, even when that caller has no idea what street they're standing on. An entire generation growing up with almost no need to learn to read a paper map because a small glowing arrow sitting quietly in their pocket always knows exactly where they are and exactly which way to turn next. None of that would have looked the same or arrived nearly as quickly without that quiet announcement in May of the year 2000, the moment a deliberately blurred picture of the world was finally allowed to come fully gently into focus for everyone, all at once. Now that civilian GPS had its full precision unlocked, the remaining challenge shifted toward the receiver itself, toward the small chip inside your phone, and the elegant, continuous calculations it performs every single second to actually turn a handful of satellite whispers into that steady, confident dot on your screen. Let's look closely at exactly what that little chip is doing right now, even as you drift toward sleep. Let's bring the whole story back down, gently, to the small object resting near your pillow tonight, and walk through exactly what happens in careful, unhurried steps every time your phone quietly figures out where it is. The very first thing your phone's GPS chip needs to do, especially if it hasn't checked its position in a while, is find the satellites at all. This is called acquisition, and it works a little like scanning slowly through the dial of an old radio, searching patiently through the pseudo-random codes. We discussed a couple of parts back, trying each satellite's unique fingerprint in turn, testing whether the tangled radio noise arriving at the antenna contains a match. If your phone has recently used GPS, it likely already has a rough idea of which satellites should be visible overhead and where to expect them, based on data it downloaded and saved from an earlier session, which lets it acquire a signal within a second or two. If it's been a long while, or if the phone has traveled a great distance since it last checked, this search can take longer, sometimes as long as 30 seconds or a minute, patiently working through the possibilities until enough satellites are found. Once the chip has locked onto at least 4 satellites, it begins the careful work we've walked through together over the last several parts. It extracts the precise timestamp from each satellite's signal. It compares that timestamp against its own internal clock, capturing the tiny sliver of travel time for each one. It multiplies each of those tiny time differences by the speed of light, producing a distance to each satellite, and it reads the ephemeris data broadcast alongside each timestamp, learning exactly where each satellite was sitting in the sky at the moment it sent that signal. With 4 or more of these distance measurements in hand, the chip performs the trilateration and clock correction calculation we discussed earlier, solving simultaneously for its own 3-dimensional position and for the small, persistent error in its own cheap, ordinary clock. This isn't a single, simple equation. It's a system of equations solved together, and modern GPS chips handle this calculation dozens of times every second, continuously refining the answer as new signals arrive. There's a genuinely elegant piece of engineering hiding in how this refinement works. Rather than throwing away the previous calculation each time and starting completely fresh, most modern receivers use a mathematical technique that gently blends new incoming data with the trajectory the receiver has already established, smoothing out small, noisy fluctuations in the raw measurements. This is part of why the little blue dot on a map app tends to glide smoothly along a road you're walking or driving, rather than jittering wildly from one slightly inaccurate point to another. With every fresh calculation, it's also worth appreciating, gently, just how much extra help modern smartphones quietly bring to this whole process. Beyond the raw satellite signals alone, your phone typically isn't relying on GPS in isolation. It often supplements the satellite data with information from nearby cellular towers, whose fixed locations are already well known, and with nearby Wi-Fi networks, whose approximate locations have been mapped by companies over years of passive data collection. This combination, sometimes called assisted GPS, lets your phone arrive at an initial rough position almost instantly, even before it has fully acquired a clean satellite fix, and lets it maintain reasonable accuracy even indoors or in dense urban canyons, where tall buildings can block or reflect satellite signals badly enough that GPS alone would struggle. There's a lovely irony worth pausing on here. For all its atomic clocks and orbital mechanics and century-old relativistic corrections, the humble little blue dot on your screen right now, the one confirming you're exactly where you think you are, tucked safely into bed, is very likely the product of several different, overlapping systems working together quietly behind the scenes. Satellites 20,000 kilometers overhead, cellular towers a few kilometers away, and Wi-Fi routers in neighboring apartments you've never met the owners of, all contributing small pieces of evidence that get blended together into one confident, simple answer. And once that answer is calculated, it doesn't just sit there. It becomes the invisible backbone of nearly everything else your phone quietly does throughout the day. It's what lets a Maps app calculate the walking time to a coffee shop before you've even finished typing its name. It's what lets a weather app show you conditions for exactly the town you're standing in, rather than asking you to type it in yourself. It's what lets photos you take get automatically, quietly tagged with the place they were taken. A small breadcrumb trail of your life that most people never think twice about. But even with all of this precision, all of this careful engineering, the system isn't perfect. There are still real sources of error creeping into the calculation, subtle physical effects that engineers have spent decades chasing down and correcting for, one stubborn complication at a time. And GPS, remarkable as it is no longer even the only system of its kind quietly circling overhead. Let's spend our final stretch of story tonight looking at both of these threads, the remaining imperfections and the growing family of rival systems that now share the sky with the original American constellation. Even with selective availability switched off, even with atomic clocks and relativistic corrections, and clever pseudo-random codes all working exactly as designed, GPS signals still pick up small, real sources of error on their long journey down from orbit. And it's worth spending a gentle moment understanding what these are, since they're part of why your position on a map is usually excellent, but occasionally, just occasionally, a little bit off. The largest of these remaining errors comes from something we haven't discussed yet, the Earth's atmosphere itself. A GPS signal, on its way down from a satellite, has to pass through the ionosphere, a layer of the upper atmosphere containing electrically charged particles, and this layer subtly slows the signal down, delaying its arrival by a small, variable amount that changes depending on the time of day, the season, and even the current level of solar activity, since the sun's radiation is what charges the ionosphere's particles in the first place. Lower down, the signal also passes through the troposphere, the ordinary weather layer of the atmosphere, where humidity and temperature introduce their own small additional delays. Left uncorrected, atmospheric delays alone could introduce errors of several meters into a position calculation. Engineers have developed clever mathematical models that estimate typical ionospheric and tropospheric delay based on known patterns, and modern GPS chips apply these corrections automatically, quietly, without you ever needing to think about it. A second source of error, one with a rather evocative name, is called multipath error. This happens when a satellite signal, rather than traveling in a clean, direct line from satellite to receiver, bounces off a nearby building, a hillside, or some other large reflective surface before finally reaching your antenna. Because that bounced signal traveled a slightly longer path than a direct signal would have, it arrives a fraction of a moment later, and if your receiver isn't careful, it can mistake this slightly delayed, bounced signal for a legitimate direct one, introducing a small positioning error. This is exactly why GPS accuracy tends to degrade in dense city environments, sometimes called urban canyons, where tall buildings on either side of a narrow street create endless opportunities for signals to bounce around before arriving. And it's part of why your phone's blue dot might occasionally seem to wander onto the wrong side of the street while you're walking through a busy downtown area. For applications demanding even higher precision than ordinary consumer GPS provides, land surveying, precision agriculture, aircraft landing systems, engineers developed additional correction systems that build directly on the differential GPS concept we touched on a couple of parts ago. In the United States, a system called WAAS, the Wide Area Augmentation System, uses a network of precisely surveyed ground stations to continuously measure the current error in GPS signals across different regions and broadcasts correction data via dedicated satellites, letting equipped receivers achieve accuracy within a meter or better, good enough to safely guide an aircraft down through poor visibility toward a runway. And GPS itself, remarkable as it remains, is no longer the only satellite navigation system quietly watching over the Earth. In the decades since GPS proved the concept, several other nations have built their own independent constellations, partly for the same practical benefits, and partly, quite openly, because relying entirely on a system controlled by another country's military carries an obvious strategic vulnerability of its own. Russia operates a system called GLONASS, short for Global Navigation Satellite System, which traces its own origins back to roughly the same Cold War era as America's transit and early GPS programs, though it followed a bumpier development path, nearly collapsing entirely during the economic turmoil of the 1990s before being fully restored in the following decade. The European Union operates Galileo, a system explicitly designed to be under civilian, rather than military, control, reflecting a deliberate choice to build a navigation system whose availability and precision wouldn't be subject to the strategic decisions of any single nation's defense establishment, the very kind of decision that had shaped GPS's own selective availability story for nearly 20 years. China operates Beidou, a system that reached full global coverage relatively recently, in 2020, completing a development effort that had stretched across more than 2 decades. And reflecting China's own strategic desire for navigational independence from foreign-controlled systems. Modern smartphones, quite sensibly, don't rely on just one of these constellations alone. Most contemporary GPS chips are actually capable of listening to signals from several of these systems simultaneously: GPS, GLONASS, Galileo, and Beidou all at once. Treating every visible satellite from any of these constellations as simply one more useful voice in the trilateration calculation, and this combined approach typically improves both accuracy and reliability, particularly in difficult environments like dense cities or deep valleys, where any single constellation alone might struggle to provide enough visible satellites. So, The sky above you tonight isn't just carrying 24 or 30 American satellites anymore. It's carrying well over 100 navigation satellites in total, launched by 4 different nations and unions, each broadcasting its own patient, whispering signal, each one, in its own way, descended from that same original insight, born from 2 curious physicists listening to Sputnik's beeping in 1957, that a satellite's signal can tell you not just where the satellite is, but where you are too. We're nearly at the end of our story for tonight. Let's spend our final few minutes together simply sitting with how strange and how quietly wonderful it is that any of this exists at all. We've come a long way tonight, from wooden ships lost on featureless oceans to a beeping metal sphere overheard by curious physicists in 1957, to atomic clocks ticking away with a precision that borders on the unbelievable, to a physicist in Berlin working out, on paper, exactly how much time itself bends around a planet decades before anyone had a use for knowing it. And somewhere along that long, winding path, this technology quietly slipped out of the world of submarines and missiles and military strategy and into something far gentler, far more ordinary, far more woven into the small, unremarkable texture of everyday life. Think about everything GPS quietly touches, most of it never announcing itself, never asking for your attention. It's in the phone charging on your nightstand right now. It's in the timestamp on your bank transactions, since, remarkably, the extreme precision of GPS atomic clocks is used to synchronize financial trading systems around the world, keeping transactions properly ordered down to fractions of a second. It's in the power grid delivering electricity to your home. Since GPS timing signals help synchronize the flow of electricity across vast networks, preventing the kind of timing mismatches that can cause cascading blackouts. It's in the flight path of the aircraft that might, right now, somewhere far above you, be quietly threading its way between storm clouds toward a distant runway. It's in the delivery driver who found your address on the first try in a city they'd never visited before. It's in the hiker who wandered a little too far into the woods this afternoon and found their way safely back before dark. It's in the ambulance that reached someone's grandmother in time, guided along the fastest possible route without a single wrong turn. None of these people, in any of these moments, are thinking about Roger Easton's quiet obsession with clocks, or Bradford Parkinson's weekend of frantic planning at the Pentagon, or the careful mathematics of trilateration, or the strange, beautiful fact that satellites tick just a little faster than clocks on the ground because gravity itself bends the flow of time. They're just living their lives, trusting, without ever quite realizing they're trusting anything at all, that a small glowing dot on a screen knows exactly where they are. That's really the quiet, understated magic running underneath this entire story. The most profound technologies, the ones that reshape how billions of people move through the world, so often end up disappearing completely from conscious awareness, precisely because they work so well, so consistently, so invisibly. Nobody marvels at GPS anymore the way people once marveled at the first telephone call or the first television broadcast. It simply is. It's just there, quietly overhead, the way the stars themselves were always quietly overhead for those long Ago sailors, staring up into the dark, wondering where on earth they might be. In a way, we've come full circle tonight. Those ancient sailors looked up at the stars and used them, however imperfectly, to find their way home. And in a strange, beautiful sense, We're still doing exactly the same thing, just with artificial stars now. 31 of them at minimum at any given moment, humming quietly along their careful orbits, patiently answering that same old, simple, endlessly important question. Over and over, tens of thousands of times every single second for billions of people at once. Where am I? You don't need to answer that question tonight. You already know where you are. You're right here, warm, comfortable, drifting slowly towards sleep, while 20,000 kilometers above you, a quiet constellation of atomic clocks keeps its patient, endless watch, whispering its steady signals down through the dark, whether or not anyone is listening. Let the satellites keep their vigil. Let the ideas from tonight settle gently, the way sand settles at the bottom of still water. There's nothing more you need to do, nothing more you need to figure out, nothing left to solve before you can rest. Just let your mind loosen. Let the thoughts drift, the way a signal drifts silently down from a satellite 20,000 kilometers overhead, patient, steady, asking nothing of you at all. And somewhere above you, quietly, faithfully, still ticking, still whispering, still keeping watch, the satellites will carry on without you all night long until morning.